Well, good afternoon. In this second section from your book, we're going to discuss annuities, which everyone's probably familiar with. If you aren't, as soon as you finish school, you will be, especially if you have taken out a loan, because a student loan is essentially one form of an annuity. So let's start with the definition here. An annuity is a sequence of payments made at regular time intervals. This time period is called the term. Okay. And it's important to note that payments into said annuity need not all be equal. But mostly they are. Okay, some more definitions here. There's a lot of definitions in the early part of this course. An annuity in which payments are made at the end of each payment period is called an ordinary. In my financial career, I've never seen anything but ordinary annuities. If the payment comes at the beginning, it's called a complex annuity. Just looking at how the numbers work, I can see why they come up with the name complex. Okay. So, more definitions. If the payment coincides with the interest conversion period, then it's called a simple annuity. Otherwise, it's complex. Okay. In this course, we study the best case scenario. So we study what? One, we're always looking at fixed terms. Two, all the payments are equal. Three, payments are at the end. So that means it's an ordinary annuity. And four, payment coincides with interest conversion period. And again, to be honest, in my career, I've never seen anything but this. So wherever these other types of annuities exist, I don't know about them. Some examples are mortgages, student loans, insurance, if you pay your insurance premiums, and like I'm doing now for retirement, savings deposits. Like every month, $100 is taken out of your paycheck and deposited into a savings account. So these are all annuities. All right, there's two real goals from this section, and goal number one is to find a formula for the accumulated amount S of an annuity, given our four assumptions above here. Okay. And so to get it part of this, we need some heavier math, which we'll look at later. But for today, let's start with an example and generalize this. So suppose that you pay $100 quarterly into a savings account for 3 years. At 8% APR or per year. And again, remember, you're putting in the $100 at the end of each term. And as you're putting it in, then the conversion period also ends. So everything's lined up. So, okay. So the accumulated amount, begins at the end of quarter one, right? And so using our formula from before, we have $100, and this is put into our. So our initial deposit goes in, and that initial $100 that goes in is computed using this. So it's at the end of term, and it's for 11 months because the first term there's nothing in it, right? Because we don't enroll until the end of term. Okay, and we're going to rewrite this as this. Okay. Okay. 3 months later, because this is quarterly, 3 months later, the second payment goes in. And what? Its growth is modeled by this number, so it's for the next 10 months. So, and we do this, right? A third payment at Q3, and it's given to be its accumulated amount at the end is this. So we do this for however long it takes, and S becomes our $100 plus we have this sum. Right, and this is called a geometric progression. We'll talk a lot more about just the standard form of a geometric progression in section 5.4. But for now, this is all we need. And so I lost my notes that quickly. This is the problem with being so organized. There it is. Okay, and the piece that we'll learn later, which isn't that big of a deal at the moment, is we wind up with this. And it's a pretty cool formula. And it looks kind of like the stuff that we were doing before. It actually comes from that. So when you have this geometric progression of, I think there's 12 terms here, right? So 3 years of 4 quarters, and you wind up with this as your accumulated amount. And if you plug this into a calculator, you get $1,341.20. So in general, the accumulated amount is R, which is your monthly payment, times 1 plus I over n to the minus 1 over I, where I is R over M from our previous work. And in this case, I equals the APR per number of compounding periods or interest conversion periods per year, and then N is going to be number of periods. Okay, so this gives us a way to accumulate an annuity. Now the other goal in this is to think, goal two is what's the present value of an annuity? So given some moment in time. The present value annuity. And so the amount invested now will have an accumulated value of this, right? And we're setting this equal to what we know is the final amount. And solving for P. And this will give us the present value of the annuity. Okay, so we do a little bit of math on this formula here. I'm going to multiply by 1 plus I to the minus n, and also do the same thing over here on this side of the equation. So that makes these guys cancel, and I'm left with P equals R times 1 plus I to the n minus 1 all over I times 1 plus I to the minus n. Okay. Now if you distribute the 1 minus I to the minus n inside here, you get a 1 for the first term, and this gives us the formula here. All right, so all I did in that step was I multiplied this guy by this, and because they're inverses of each other, I get 1. and then I multiplied it by this, and I just get 1 minus I to the minus n. So this gives us a way to compute the present value of our annuity. So let's look at a couple of examples here. All right, this is a fun problem because it reminds me of my own situation. I bought my first car, new car, and I did a 5-year monthly payment plan because the interest rates are less than 1%. And I'm paying it off next month, so I'm on my last payment. Pretty happy about that. All right, let's say you're buying a car. And you put a $6,000 down payment. In today's economy, that's probably not a good move, but whatever. And then let's say you're paying $600 a month on a 3-year loan at 6% APR, which is really high now. You'd only get a 6% APR if it was your first car or you had bad credit. Okay? And this is compounded monthly. So you're paying monthly, you're compounding monthly. It all happens at the end. And so question 1 would be, what was the original cost of the car? And also, at the end, how much interest? Did you pay? Okay, so we're computing present value here. So P is going to be R times, get the right formula here. One minus 1 plus I to the minus n over I. So what did we do? We put in $600 monthly. And what is I? I'll make a little sub thing here. I is going to be R over M, which is 0.06 over 12, which is 0.005. So this is 1 minus 1.005 to the minus 36 all over 0.005. You plug all this into your calculator and you get $19,723. Okay. And so we're going to add 6,000 to this because that was our down payment. And we get $25,723. Right, so how much was the interest? Well, the total payout was 36 months times 600. Right. So after you did your down payment, which wouldn't affect the $21,600, and you actually only were supposed to pay $19,723 for a net difference of $1,877. So this is how much you paid in interest over 3 years. Okay. Okay, let's do another example. So let's say every year on January 31st, so the first pay period after the start of the year, you make a $2,000 contribution to an IRA. Which is earning interest at 5% per year. So assuming you work for this company for 25 years before retirement. So after 25th payment, how much money do you have for retirement? And this basically says, how much did you accumulate, or what is S? So S turns out to be, so you put $2,000 a month in. This is 1 plus 0.05 for 25 years, or 25 compounding periods, divided by this guy. And it's around $95,454. Okay. Enough to last you, 5 years or so if you're lucky. Hopefully there's something else going on, like a good pension. Okay. So by now we've had homework 1 turned in, and now this is going to be homework 2, part 1. There's going to be a second part that comes on Thursday. So this first part is from section 5.2, and it's problem 6, 11, 20, 22, 27, and 28. And all you're doing is really thinking, reading, and applying these 2 formulas. The interpretation is everything. All right, well, I'll see you in a few minutes for some more examples.